We talked about infrared, optical, ultraviolet earlier. And what we will try and do briefly is to have a look at the telescopes and techniques in terms of observing at these wavelengths. And the first thing I would like you to do is have a look at this image. Yeah, okay. This is a galaxy NGC 3370. It's about 98 million light years away. It's towards the constellation Leo. It has a diameter of about 100,000 light years, which is very similar to that of our own galaxy. The mass is about 10 to the power of 11 solar masses, which is also similar to our own galaxy. And as you can see from the images, that it has an intricate spiral structure. I want you to tell me what are the striking differences you see between the image on the left and the image on the right. Any one of you can unmute and say.
The clarity of the image is very different.
The clarity of the image is very different. Okay.
And there's also a lot of surrounding stars that are visible on the right, but not on the left.
Surrounding stars are visible on the right and not on the left.
Or stars and some of the galaxies are also better defined on the right.
Okay, but many more
also,
objects on the right.
The right one lacks a supernova or a bright star.
Very good. The right one lacks a supernova and the right star. Okay. So you'll have got all the main features of the difference between the left and the right image. This is a galaxy where a supernova went off in 1994. Supernova, the way they are named is ascend, year, and combinations of letters. And you can see that over here, the supernova is missing. But in terms of imaging, the essential differences are what you'll have pointed out, that the right one looks much sharper, and it also has many more objects which are visible, many more objects are visible. And even in objects which are visible, for example, this galaxy over here and this galaxy over here, you can see sort of some kind of spiral structure associated with it. And you can see many more objects over here. This is an image made with the Hubble Space Telescope, okay, in 2003. And this is from a ground-based telescope in 1994 when the supernova went off. Now, so what is it that we want to achieve with a telescope? For example, if you want to look at with a telescope, ideally what you want to be able to do is be able to detect faint features, and you also want to be able to see finer features in a galaxy. Okay. Now that is what a telescope basically enables us to do. And as we saw in the history of astronomy sort of interaction, that although often attributed to Dutch optician Hans Lippershey, who sort of put lenses together, but Galileo was the one who really sort of put together and demonstrated his utility in terms of astronomical observations and made several sort of important discoveries. So what the HST image or the telescope you want to do is to see finer features and to be able to see faint objects. Objects will be fainter. They could be intrinsically faint objects, which you want to study, or they could be objects which are luminous, intrinsically luminous, but very far away. And so the amount of light that you receive or the amount of radiation or energy that you receive from the object could be very low. So the two important aspects are the angular resolution and the sensitivity. While mentioning about angular resolution, it is true that while you look at the galaxy, you want to look at individual stars, but there are also cases, situations where you want to look at diffuse extended emission. And if you had very high angular resolution, you may miss that. There's a lot of interesting physics to be learned from diffuse extended structures as well. We will see many examples of these, but just to give you one example right now, for example, clusters of galaxies have extended halos and relics of emission around them. And if you were to observe with very high angular resolution at radio frequencies, for example, you will completely miss them. Similarly, for example, you would have seen the image of the black hole in M87, the Event Horizon Telescope, made with micro-arc second kind of resolution, that you don't see the extended emission at all. So so you have to tune your angular resolution to also your astronomical issue or the problem that you're trying to study. but generally it is true that that one of the objectives of a telescope is to actually be able to look at finer structures and be able to see with high angular resolution. Now, just a few small definitions over here, something which you would be familiar with from basic optics. And there's a very nice sort of video which we had recorded earlier. I've given a link over here by my friend and colleague from Ayuka, Professor Ram Prakash. You could listen to that. And I've taken a few things from his video as well. And now let's consider that there are two objects in the sky, okay? Two objects in the sky, which are close by, maybe separated by an angle theta, and they're both giving off radiation which you detect. If you were to take the first source initially, a star say, it will emit radiation in all directions. It will come out as a spherical wavefront, but because you are so far away from the source that it will effectively be a plane wavefront to you. Similarly, the second star, which is displaced by, say, a small angle, angle theta, will also emit spherical waves, but those spherical waves will also travel out. And by the time it reaches your telescope, it will be a plane wave, but it will be inclined at a small angle. Okay. Now let's look at the most basic basic telescope. It's just a lens over here. You'll require an eyepiece over here to be able to see the image. And depending on the focal lengths, you'll get a certain degree of magnification. But let's just focus on this convex lens over here. And from simple ray optics, you will know that they will focus to a point at a focal plane, right? And the dark colored and the light pink colored rays show the difference between the two wavefronts from the two neighboring stars in the sky. When I say neighboring, it need not be physically neighboring. It is just that they appear closer together on the sky plane. So they're separated by a small angle, say theta. Okay. Now let's look at the system. Here, for example, you have a lens which has a size D. Okay. This is what we effectively refer to as the aperture or the size of the telescope. Aperture of diameter D, and the area of this is D squared. Okay. And this is effectively decides how much light you receive from it. So if you had a larger mirror, for example, you would be able to receive a larger lens. There would be more photons which it will intercept, and you'll be able to gather more light. Okay. So the rays, this lens focuses the lights on this focal plane, and where it sort of focuses will depend on the focal length of the lens. Now, the ability to separate these two objects out in your focal plane would depend upon the focal length of the telescope. So for example, I can measure it by the plate scale, which is given by P, and you can see from this expression over here that this separation between the two images on the focal plane H is equal to f theta. Okay, f is the focal length over here, and theta is the angular separation over here, and this is a small angle approximation, and this will lead to theta is equal to h upon f. This will be in radians, so I can translate that into arc seconds, and I can express this as 206,265 upon m. And if I were to put h in millimeter, the plate scale is arc seconds per millimeter. So in 1 millimeter of separation, what is the arc second separation that you will be able to perceive in the sky? And you can see that once you increase f, okay, once you increase f, that your resolution is going to get better. You'll be able to resolve or see sources at smaller separations in the sky. So in terms of being able to see or get adequate separation in your whatever detector you put over here, whether it's a photographic emulsion or whether in modern times it is all a CCD. In Galileo's time, it was just the eye. That if you had a higher focal length, you'd be able to see finer details for f to be larger. So you can see it over here also. When f is larger, that the arc seconds per millimeter is going to go down depending upon what f is. And because we have taken h to be 1 millimeter over here, f would have to be in the scale of millimeter. The other definition, which often refers to, you'd be familiar from your cameras or or telescope as well, if you've used amateur telescopes, is the focal ratio. Focal ratio is focal length f divided by the diameter t. I put this in italics f, whereas the focal length is the standard f over here. Okay, and the other terminology which you will meet is the magnification, where f is the focal length of the objective, that is over here. And here I've just put the focal plane shown over here, but normally you'd observe with an eyepiece over here, and that is the focal length of the objective of the primary divided by the focal length of the eyepiece will give you the degree of magnification of the lens. And this is often written as f oblique n, where n is the number where focal length is divided by t, right? So this is something you would be perhaps familiar with, but this is just to recap that the focal length plays an important role in able to distinguish images on the sky, images on the focal plane over here. So the higher the focal length, your better would be that ability. This actually shows you the same sort of thing which you discussed earlier, that this is the eyepiece over here, which I hadn't drawn over there. I just shown the focal plane over here, that if you had a smaller FE over here, because magnification is the angular size of the object, the ratio to two angular sizes over here, theta what you observe and theta what it is incident at, and magnification is given by the focal length of the objective divided by the focal length of the eyepiece. And you can see this is just illustrates that you, by saying that if you had a smaller focal length, you'd see a much enlarged image of Jupiter. Whereas if you had a longer focal length, you would see a smaller image of Jupiter. So magnification would be smaller. And this just gives you an illustration which you can look at it yourself about the derivation of this magnification effect that you get by observing with an objective lens and an eyepiece over here. One should also notice over here that with this eyepiece that you're seeing much more of the background, whereas here you're seeing less of the background and much more of the image, getting a closer view of the image. Okay, but that is what, in terms of being able to resolve or see images clearly on the focal plane by whatever the detector that you might have. Now, but for a single point source, the resolution is ultimately given by the Rayleigh's criterion. For example, if there are 2 point sources which are close together, you would be able to resolve them depending upon the angular resolution of your antenna. And angular resolution of your antenna, including your eye or any telescope, is given by the size of this disk over here. Okay, this is the Airy pattern, because when you receive a ray from infinity, you don't really see the entire ray. You block off a part of the ray with the lens or the antenna or your lens in your eye, and they would interfere and produce this diffraction pattern, which was worked out by Airy, and is known as, and this disk is known as the Airy's disk. Now, if there are 2 objects which are very close together, okay, very close together, if the resolution is larger of the instrument than what you can resolve, you will not see these as 2 different objects, but as one single object. Okay, so 2 point sources are resolved from each other if they're only separated from each other by at least the radius of the airy disk. And the airy disk contains about 84% of the light. And the resolution limit is set by when the maxima of one falls on the first minima of the other. So this is again something which you'd have learned from your basic optics. This is just to remind you that the resolution of any piece is given by 1.22 lambda by d in radians. Okay. Now, what do you think is the typical resolution of your eye, of the human eye? Anyone? So, you can derive it by applying this equation. Okay. In addition to the diffraction limited resolution that is called, that is the best that you can get given the size of your aperture. So you can see it's 1.22 lambda by d. So the longer the wavelength, that poorer would your resolution be. And again, it's divided by d. So the smaller your lens or the smaller your antenna for radio astronomers, the coarser would the resolution be. Okay. But in addition to the limits set by diffraction, the atmosphere also plays a role in the kind of images that we get. Obviously, how deep we can see would depend on the sky background, and dust and molecules scatter light from the cities, from the moon, which affects the amount of light over there. Then there is also atmospheric extinction, because the dust and molecules in the atmosphere scatter and absorb light from the astronomical source of interest. And that is something one corrects for while getting magnitudes of these objects. Transparency of the atmosphere, absorption of light in the atmosphere. And the important aspect in terms of resolution is the turbulence in the atmosphere. Okay. So what happens is, because the atmosphere is turbulent, the ray doesn't come out straight, but it could be corrugated. Okay. So what that effectively means that your image tends to get blurred. And it gets blurred depending upon how bad the Earth's atmosphere is in terms of its turbulence. So if you had an ideal point source, it can get scattered, looking like a Gaussian. And in a good site, the full-width half maximum would be roughly of the order of 0.5 arcsecond, or sometimes even slightly better. Okay. But on the other hand, when you calculate what you would get from applying Rayleigh's criterion, you would get a much smaller value. If I take a human eye, the pupil diameter is, during the day, it is smaller than during the night. And you will notice that when you're actually put the lights off, it takes a little time to get adjusted to the darkness. Then your eyes sort of, the pupil diameter increases, and you can see more things even after the lights are off at night. So that changes depending upon the quantity of light in the surroundings. And optimal wavelength, I've taken it as 0.55 microns. I'm using different things just to get you used to it. We have used nanometers and angstroms, and I've used microns over here. Then I written down for 1.2 meter telescope at the Whipple Observatory, Fred Lawrence Whipple Observatory, again at the same wavelength, and a 2.4 meter Hubble telescope. Now, if you look at it, if you apply that formula, you can verify it for yourself later in case I've made any algebraic mistake. And that for the eye, it's about 46 arcseconds, but it varies, as I said, depending upon day or night. So in the ballpark of about a minute. When you take the 1.2 meter, it's about 0.12 arcseconds. And for the Hubble Space Telescope, it is about 58 or 60 milliarcseconds at this particular wavelength. At shorter wavelengths, it'll be even finer than that. But as we just mentioned, that seeing conditions limit the telescope. For example, for a 1.2 meter telescope on the ground, unless you adopt very advanced techniques of what are called adaptive optics and active optics, where you try to correct for corrugation of the wavefront due to turbulence in the atmosphere, you'll get typical resolutions, which is given by the seeing conditions in the site. As I said, 0.5 arcsecond is not a bad site. Whereas in the Hubble Space Telescope, you would get the diffracted limited resolution as well as long as your optics is okay. Remember in HST also, there was some problem with the optics initially, and there was a mission to correct that. And your angular resolution of the Hubble Space Telescope, which is not affected by the atmosphere, would be close to that of the diffraction limit, limited resolution, which you get by applying Rayleigh's criteria for resolution. Okay. There are two other little sums that I was also going to give you, but you can do that yourself later. But we'll just quickly mention what is involved. Consider a 20 centimeter telescope with a focal ratio f/8, observing at a wavelength of 550 nanometers. Again, what I've asked you to do is estimate the diffraction limited resolution and how this translates to millimeter in the focal plane. And the second one is a 6-inch f/5 telescope, okay? And an eyepiece with a focal length of 25 millimeters. And as you see that, although in larger telescope, normally we talk of centimeters and meters, amateur astronomers still use inches in terms of describing their telescopes. It's quite common to say it's a 6-inch telescope or a 3-inch telescope. And I want you to estimate the degree of magnification. So this is just applying the equations we sort of saw a little while earlier, and you can do that at home later. I've done it over here, but maybe you can just try it at home.